Hey guys, welcome to the first video of the Digital Logic series. Today we will be going over a question from the textbook, and it states, give the binary, octal, hexadecimal, and decimal values for the following unsigned numbers. But before we get started, I'll explain what exactly is binary. So the way we read numbers as humans is in a base 10 world, and this is very intuitive for us, except it's not very efficient for digital systems. At the hardware level, computers are just large networks of transistors that act as switches. And a switch only has two states. This could be on off, this could be high or low, this could be true or false, things like that. And that's when we would be using binary. But the problem is that long strings of one and zeros quickly become difficult for humans to read. And we have things like octal, which is base 8, and hexadecimal, which is base 16, and that's where things like that can come into play. They aren't really different type of math. They're simply just shorthand representations of binary. So for example, as we'll see coming up, one hexadecimal digit can represent exactly 4 bits of binary. So today what we are going to do is look over how to translate between these systems. So we'll go ahead and get started. For the first example, we have 735 starting in a base 10 form. So the easiest thing to do first is convert from decimal to binary. And to do this, we'll use what's called the successive division method. We will divide our target base by 2, record that remainder, and then repeat until the quotient hits 0. So we'll go ahead and get started. 735 divided by 2, this will get us 367 with a remainder of 1. And as the title states of the method, it's called successive division. So we're just going to keep dividing that number that we got. So 367 is our next number to divide, and we'll divide that by 2. This will get us 183 with a remainder of 1. 183 divided by 2. This will get us 91, remainder 1. 91 divided by 2. This will get us 45, remainder 1. 45 divided by 2. This gets us 22, remainder 1. 22 divided by 2 equals 11, remainder 0. 11 divided by 2 equals 5, remainder 1. 5 divided by 2 equals 2, remainder 1. 2 divided by 2 equals 1, remainder 0. And again, we're not finished yet. We still have to divide that 1. So 1 divided by 2 will get us 0 in this case with a remainder of 1. So the division is finished. A couple things to note here first is what is the most significant bit and the least significant bit. The one we just finished at the end, which would be right here, we will be calling our most significant bit. And at the very top, the one we started with here, this is what's called our least significant bit. And this is very important when it comes to how do we actually write the final answer. So the final answer, what we will do, writing from left to right, we will start with our most significant bit, which will be 1 and 0. 1, 1, 0, 1, 1, 1, 1, 1, and that's 5 zeros. So this right here is how we got our final answer for the decimal form, and we will put a subscript 2 there just to show that that's in decimal. Okay, so done with the first part. Then what we'll do is go and get the answers for the octal form and the hexadecimal form. And to do this, you are able to use the successive division method and divide by 8 and then carry the remainder, or divide it by 16 and carry the remainder, except there's a shortcut here, and that's called the bit grouping shortcut. So that's what we'll use. We'll take this number that we just got and we'll group it into groups of 3 for octal or groups of 4 for hexadecimal, and then we'll reference the table on that. So rewriting the number, we have 1, 0, 1, 1, 0, 1, 1, 1, 1, 1. We'll start with octal. We'll do it in groups of 3. So we'll group these 3 bits here, these 3 bits here, these 3 bits here, and you'll see on the very left that we only have 1 bit, but what we can do is add imaginary zeros here to complete the bit. So now that we have all the bits grouped, we'll go ahead and look at this table over here, and we'll fill in the numbers. Starting from the right, we see 111. That corresponds to number 7 down here, so we'll write 7 underneath. Next, we have 011. 011 will correspond to 3, so we'll write 3 underneath. And then right next to that, we have another 011, so we'll write 3. And then for the final one on the left, we have 001. That corresponds to the number 1. So we'll write 1 underneath there. The final answer will be 1337, and then we'll write subscript 8 to show that that's in octal form. And then for the final step, which is finding our hexadecimal form, we will do the exact same thing. Instead of grouping in groups of 3, we'll do it in groups of 4. So we'll rewrite the number 1 0 1 1 0 1 1 1 1 1. But instead of using the octal table, we'll use what's called the hexadecimal table. And we'll make those groups of 4. Before here, and same exact thing as before, where if we're missing 2 zeros, we can fill it in to get that final group. So 1111, we see that that corresponds to the letter F. Then we have 1101, which corresponds to the letter D. And then 0010, that corresponds to 2. So our final answer for this in hexadecimal form will be 2DF with a subscript of 16. And that is the final answer for the first part. We will be starting in octal form, and we have 272. So the fastest pipeline is to go through binary first, and then we'll hit everything else right after that. So to use the table, we'll unpack each octal digit directly into its 3-bit binary equivalent. What does that mean? That means using the table, we can break this number into 2, 7, 2. We see here that 2 corresponds to 0, 1, 0, and we see 7 corresponds to 1, 1, 1. So if we combine these numbers together, we will get 0, 1, 0, 1, 1, 1, 0, 1, 0. And if we put a subscript 2 there, that's our final answer for binary form. Then take that binary string and regroup it into sets of 4, starting from the right. This is how we'll get our hexadecimal form. So if we rewrite our number, 0, 1, 0, 1, 1, 1, 0, 1, 0, we can reference that hexadecimal table and make those groups of 4. And you'll see that the leading term on the left side is just a 0, so we can cross that out. We don't have to worry about that. Starting with the first term here, we have 1, 0, 1, 0. This becomes an A. And we have 1, 0, 1, 1. This becomes a B. So our final answer in hexadecimal form for this will be BA. Okay, and then one more step. This is how we get the decimal form. We will use what's called a positional weight. Since we have the first number in octal form, we can write that out, and then the positional weight will be 8, or different powers of 8. So we will do, for the first one, 2 multiplied by 8 to the 0th power, 7 multiplied 8 to the first power, and then 2 multiplied by 8 to the second power. And the reason we're using 8s is because you can see over on the initial question that the power, or the form, is in octal, which is 8. If this were in hexadecimal form, we would be multiplying it by 16. So to add all the math up, we will do 2 multiplied by 8 to the second power plus 7 multiplied by 8 to the first power plus 2 multiplied by 8 to the 0th power. If you perform all the math, we will get 128 plus 56 plus 2. This gives us a final answer of 186. And don't forget to add that subscript 10 to show that this is in decimal form. Okay, moving to the next example, we will be handling fractions in binary. The integer rules apply to the left of the radix point, but for the fractional part to the right, your positioning moves left to right. So we'll explain what that means in a second, but first we're going to go rewrite the number. So it'll be 10110.0101. So the first thing we're going to do is convert this into octal by making them into groups of 3. So we'll start with this group here, and then there's 2 missing zeros that we can add in, and that's our decimal. Next, we'll group starting at the decimal point going to the left. That's our first group, and then we have a missing 0. We'll add that in, and then we have groups of 3. So we see the first one is 0, 1, 0, 1. Sorry, the first number is 0, 1, 0, and this becomes 2. Then we have a 1, 1, 0. This becomes 6. For the decimal point, we have 0, 1, 0. This becomes 2. And then 1, 0, 0. This becomes 4. So our number in octal form will be 26.24. And then to get this into hexadecimal form, we will do the same thing except group into groups of 4. So rewriting the number 10110.0101. This is our first group of 4. This is our second group of 4. And then filling in the imaginary zeros. That is our third group of 4. So if we use our table here, we see the first number is 0001. This corresponds to 1. Then we see our second term, which is 011. This corresponds to 6. And then our decimal point, and then the final number, which is 0101. This corresponds to 5. So our final answer in hexadecimal form will be 16.5. Okay, and then one more thing to do. We will convert this into decimal form. To do that, we will use the same steps that we used for the last problem. We will rewrite the decimal number out, which is 10110.0101, and then we'll multiply from numbers of base 2 and powers that follow the terms. So we will do 0 multiplied by 2 to the 0, 1 multiplied by 2 to the first power, 1 multiplied by 2 to the second power, 0 multiplied by 2 to the third power, and then 1 multiplied by 2 to the fourth power. When going to the right side of the decimal point, same exact thing, but we'll use negative powers. So this will be 0 multiplied by 2 to the negative first power, 1 multiplied by 2 to the negative second power, 0 multiplied by 2 to the negative third power, and 1 multiplied by 2 to the negative fourth power. Anywhere there's zeros, you don't have to worry about the term because it will just be 0, so we'll cross out the zeros. So leaving that behind, we will get 1 multiplied by 2 to the fourth, plus 1 multiplied by 2 to the second, plus 1 multiplied by 2 to the first, plus 1 multiplied by 2 to the negative second power, plus 1 multiplied by 2 to the negative fourth power. So doing all the math on this, we will get the answer as 22.3125 base 10. Moving to the final problem. We will start with 16.5 in hexadecimal, and we will convert that into binary, octal, and decimal form. So first step to do here is rewrite the number out. And since we know it's in hexadecimal form, we can straight away go to the table. We see in the table that number 1 corresponds to 0001, number 6 corresponds to 0110, and 5 corresponds to 0101. So straight away we can convert this to decimal by just using the table. So it will be 0001, then using 6, which is 0110, decimal point, and then 5, 0101. So this is our first answer in binary form. So once we have the binary form, we can group this into groups of 3 and get our octal form. So we'll rewrite it out as 0001, 0110.0101. Make those groups of 3 and add the zeros when necessary. Any extra zeros we can just disregard. So now moving to the octal table, we see in the beginning that 010 will correspond to 2. 110 corresponds to 6, decimal point. 010 corresponds to 2, and 100 corresponds to 4. So the final answer in octal form will be 26.24. And then one final step here, we want to convert it into decimal form. So we will rewrite the binary number out. And we'll use the multiplication. So multiplying 0 by 2 to the 0, multiplying 1 by 2 to the first, multiplying 1 by 2 to the second, multiplying 0 by 2 to the third, and multiplying 1 by 2 to the fourth. And then same thing on the right side except negative exponents. 0 multiplied by 2 to the negative first, 1 multiplied by 2 to the negative second, 0 by 2 to the negative third, 1 times 2 to the negative fourth. Crossing out the 0 terms, and then adding the numbers. This will be 1 multiplied by 2 to the fourth, plus 1 multiplied by 2 to the second, plus 1 multiplied by 2 to the first, plus 1 multiplied by 2 to the negative second, plus 1 multiplied by 2 to the negative fourth. Okay, completing that math, you will get 22.3125, and this will be in base 10. And that is your final answer. Okay, that's all for this video on workflow for unsigned number systems. Thank you all for watching. If you have any questions on how to handle these conversions or suggestions for a specific problem style you want to see next, just leave that in the comments below. Make sure you check out the other videos on the channel if you need any additional help. See you in the next one.